Today we will talk about the design of foundation topic. This is a topic which comes after the bearing capacity and settlement, which we have discussed already with engineer Mustafa in the tutorials, the last tutorials. Today we will talk about a new chapter regarding the design of foundations. This part we will talk about the design of shallow foundation and deep foundations. First of all, we have to know that foundations are divided to two main parts. Foundations are divided either to shallow foundation or deep foundations. Those are the most common two types of foundations. When we talk about shallow foundations, the footings are placed over the soil directly. As you can see, the footing is placed directly above the soil surface, and it is used when the bearing capacity of soil is high and the settlement is low. This is the first type, and we have already talking about this type in the bearing capacity and settlement. The other type of foundation, when we are talking about weak compressible layers in the surface top layers, then I cannot place my footing above the soil because there would be problems in the settlement and the bearing capacity, which cannot sustain the load of the superstructure. So I have to transmit the loads into bearing layers extended to a certain depth using deep foundation member. And the most common type, which we will already discuss in our course, is the piles, which I'm drawing here in the section. So in that case, I'm transferring the load of the superstructure to end bearing layer, extending through weak compressible layers. Okay. So today we will talk about the first shallow foundation types. Shallow foundation means that in most cases the ratio of depth of foundation to the lesser dimensional footing is less than 1 or equal to 1. And on the other hand, the deep foundations, we are talking about depth of foundation over B is greater than 4, not 1, because there is type of foundations intermediate between these two types. Okay, anyway, so first of all I have to determine the dimensions of footings and the thickness. When I'm talking about the design of foundation, this is a cross section. Okay, I need to determine the thickness. I need to determine the dimensions of the footing to transfer the load of the column applied on it safely on the ground without causing excessive settlement in the soil or without causing shear failure or bearing capacity failure in the soil. In isometric, I have a certain column like that, which carries certain load from the superstructure, and it is placed over a footing like that. The design of foundation means determine the width and the length of the footing and the thickness and reinforcement, because it's a reinforced concrete member, so I need to determine the reinforcement details in that cross section as any other reinforced concrete member talking in the RC course, like columns, like beams, slabs, whatever type of members. So these footings are constructed under columns to transfer column load, P column, as you can see, okay, into the ground surface. So first of all, I need to know what are the data required to design a footing or shallow foundation system. Also, I need to mention that shallow foundation have different types. When we are talking right here, shallow foundations, there is type called strip footing, for the walls or retaining walls, strip footing, and isolated footing, the second type, which I have already drawn the isometric in the previous page. Isolated footing means that each column in your structure is constructed over an isolated footing. The third type is combined footing, and the fourth type is called strap footing, and the fifth type, which is also most common, is the raft or mat foundation raft. Those are the types of shallow foundation. Which I am highlighting in yellow is inside our course this year, the isolated and the strip foundation. But for your information, that you need to know that there is combined footing, there is a strap footing, there is raft foundation. In the normal conditions, we were discussing the combined footing and the strap footing, but the raft is out of scope already. It has certain type of analysis on computer, or it can be already analyzed manually, like flat slab or whatever. There is different types to analyze raft, which is out of scope this section or this tutorial. Okay, so we will talk about isolated footing, and what we have already talking about isolated footing is the same for strip. Strip is so easy compared to isolated. If you understand well isolated, the concept of analysis of isolated footing, then it would be so easy to deal with strip foundation. Okay, first of all, I have to know the column loads which I'm designing the footing of. You know that any design of any proposed structure, you have to design the superstructure, the part of the building above the ground surface, and determine the loads of columns based on the function of the building and the number of stories of this structure and whatever else. So you can determine the column load, and if you have the column load, you can determine column dimensions. Secondly, allowable net bearing capacity. We have talking about the bearing capacity in the last sections with engineer Mustafa, how to determine the allowable net bearing capacity, which can the soil sustain. Thirdly, we need to know the material properties. As we have already discussed, the footings are reinforced concrete member composed from concrete and steel, and the strength or the grade of steel and the strength of concrete are determining the parameters used to determine the thickness and reinforcement, represented by the parameters K1 and K2. Those are two parameters which are used in the determination of the thickness and the reinforcement. So let's take an example and move on and discuss how can we analyze an isolated footing and determine its dimension, reinforcement and thickness, and drawing section showing reinforcement details. Let's assume having column load equal to 250 tons. This is a column load 250 kilonewton. Wait just a minute, I'm searching for this example. The column load is 250 tons and dimensions 30 by 80 centimeters. The allowable net bearing capacity in this construction site is equal to 2.5 kilogram per centimeter squared, and you have to notice that there is difference in units between the tons, the column load and the bearing capacity. And he is talking about the compressive strength of concrete is 300 kilogram per centimeter squared and steel grade 36/52, which gives K1 and K2 values for the working stress design method to determine the thickness and the reinforcement. K1 0.246 and K2 is equal to 1543. Those are the parameters used to determine the thickness and steel reinforcement using the working stress design method. Okay. It is required to construct these foundations. So first of all, I need to determine the area of the minimum required area for this footing. I have now this column 30 by 80 centimeter, carries 250 tons column load from the superstructure, and this is the footing which I need to design now. Excuse me for this unorganized drawing, but it's a sketch. I hope you can catch with me. So I need to first of all determine the width and length for this foundation to ensure what? To ensure that the contact stress under the foundation, is less than the allowable net bearing capacity. I need to ensure that the contact stress between the footing and the underlying soil is lesser than or equal to the allowable net bearing capacity, to ensure that the column load is transmitted safely to the underlying soil without having excessive settlement or bearing capacity failure, as we have already discussed the two main conditions for proper design of shallow foundations. Okay, this is ensured by determining area required. I need to divide column load over Q allowable net, and you have to be aware that there is different units for if you can see here, this is in 250 tons and this is here kilogram per centimeter square. So I need to transfer one of these values to the other unit, and there is a conversion unit if you wish to know units. 1 megapascal, which is equal to Newton per millimeter square, is equal to 10 kilogram per centimeter squared, is equal to 100 ton per meter square, which is equal to 1000 kilonewton per meter square, or kilopascal. They are the same. So you have to know these conversion units. I am highlighting in yellow. Okay, take care of this, and you have to know it well, this line. Okay, so if I need to transfer 2.5 kilogram per centimeter square, it will be 25 ton per meter square, and the column load is 250 tons, so the minimum required area is 10 meters square. Okay, 10 meters squared is the area of the rectangle I need for transmitting the load of column 250 to the underlying soil. First of all, I have certain conditions I need to fulfill. The footing shape in the plan resemble the column shape. So as you can see, the long side of the column coincident with the long side of the footing, and on the other hand the short side with the short side. And the extension of foundation is the same from all the sides of the column, and we can assume it X. As you can see, the extension of the footing is the same from all the column sides, X, as you can see. So the dimension of the foundation required to determine is based on the column dimensions 0.3 plus 2x, right here 0.3 plus 2x, and the other hand 0.8 plus 2x. I assumed a certain extension for the footing x from all sides of the column toward the edges of the foundation underlying the soil. Okay, I can see that 10 equal to the area 0.3 plus 2x multiplied by 0.8 plus 2x, and I can solve this equation and determine x, which will be 1.31. X is equal to 1.31 meter. Due to construction, I have to approximate the values to the upper 5 centimeter to be easily constructed at the site. So I will assume it 1.35 meters. So in that case, I will get the P actual and L actual and substitute for this equation, and I can find that it will be 3 meters and this 3.5 meters. Those are the actual dimensions required to sustain the column load specified in our example. After determining the actual dimensions, I have to determine the actual stress. Q actual is equal to column load over P actual L actual. P column, which is equal to 250, L column, L actual and P actual 3 by 3.5. So Q actual in that case will be 23.8 ton per meter square. You have to notice that this actual stress is less than or equal the allowable bearing capacity, the allowable net bearing capacity, which was 25 ton per meter square. So I finished the first step regarding the geometric design of foundation. I have determined the dimension to ensure the transmission of the load safely on the underlying soil. Secondly, I need to determine the reinforcement and the thickness, and this is concerned with the structural design. Structural design, I have to deal with the foundation as a reinforced concrete member, which I need to determine the straining actions. As you can see, I will take a strip 1 meter, as we can as we have already done in the analysis of slabs in the reinforced concrete course. I can take a strip 1 meter right here, as you can see in the plan, or in the other direction. It doesn't matter in that case. It doesn't matter in the design of isolated footing if you take a strip in that direction or the other direction, because the extension of foundation is the same around all sides of the column. Okay, so there is no difference between the two directions. Each one will have the same straining actions. This is strip 1 meter, and this is a strip also 1 meter. Okay, after I have already taken a strip 1 meter, I will draw the cross section. The extension here I have determined 1.35 meters. I have reaction from this underlying soil on the footing. I have taken, as I have said, 1 meter strip perpendicular to the plane I have drawn. So the actual stress here 23.8 ton per meter run. Okay, first of all I need to determine the moment. There is a critical section where we can calculate this value. It is on the edge of the column, this position. So if I wish to calculate the moment critical, so it will be Q actual multiplied by x squared over 2, and Q actual you have its value 23.8, and x we have also its value 1.35. so when I calculated this value, it comes out by 21.7 ton meter, and this moment per meter run of the foundation. So in the next step I will determine the depths required, K1 square root m over b, and I need to ensure that the values given for Q1 and Q2 must be used with the units for moment kilogram centimeter and the lengths in centimeter. So b is equal to 100 centimeter, and moment critical I can transfer it to kilogram centi by multiplying by 10 power 5. So I will find out the depth is 36 centimeter. I need to know that we are designing rigid foundation which requires minimum thickness of 40 or 50 centimeter. Let's assume I use 50 centimeter. So the depth will subtract the cover of 7 centimeter, for example. The cover, by the way, from 5 to 10 centimeter. So I will remove the cover 7 centimeter, will be 43 centimeter the depth. This is a D actual, and hopefully it is greater than D allowable. D minimum. D minimum, which I got from this equation. So this is the first criteria to determine the depth of foundation, to determine the moment at this critical section and move forward, proceed. The second item I need to ensure is the shear or diagonal shear or one-way shear, whatever. I have the same cross section with the underlying reaction of the soil, 23.8 ton per meter run. In that case, to determine the shear, the critical section for the shear is at distance d over 2 from the face of column. as you can see, d over 2 from the face of the column, d over 2 which I have already estimated in the previous step, which was around 26.5, which will be 26 is good value now. So I need to determine the shear. As we have discussed in the structural analysis, you can calculate it from the right or the left. It will be much easier to calculate it from the left. As you can see, Q critical will be Q actual multiplied by X minus D over 2. So Q critical in that case, I have calculated its value, and it was 27 ton per meter run. Then I estimated the shear stress, critical shear stress. I took the critical shear force over the area resisting this shear force is equal to 1 meter width of the footing, as you can see in the cross section, multiplied by the depth of footing. This is the area resisting the shear force. So this is 1 meter times the depth 0.43. So you can calculate it, as you can see, 63 ton per meter squared. I need to compare this value with the allowable value is fixed 35 ton per meter squared. It's fixed in our course. It's variable in practical according to the strength of concrete, because we don't use any shear reinforcement for the foundation. We depend only on the thickness of concrete foundation to resist shear force. Okay, so what means that the critical shear stress is greater than the allowable? I have to maximize or increase the thickness of footing. The thickness assumed 50 centimeter is not sufficient to resist the shear stress. So what I can do, I can put here the allowable shear stress and get the depth, the approximate value or the guide value for the depth. Okay, otherwise I need to try certain cycles, try thickness equal to 60 centimeter and check, try thickness 70. At each cycle you have to increase the thickness 10 centimeter, try thickness 70 centimeter and check, try 70. And if it's not safe here, so you have to increase. At 80 centimeter the depth, I subtracted 7 centimeter cover. I estimated the critical shear force. You have to know that the critical shear force will be different at different depths for the footing. It will be 23 ton per meter run. Critical shear stress, in that case, is 32 ton. Hopefully it is less than the allowable. So I ended the shear moment, the two cases for the proper design of isolated footing. The next step is to check the punching. Check punching of the column. If I have, by the way, different extensions for the footing around the column sides, then at that case I need to ensure the analysis of the two directions of the footing. I need only to analyze one direction if it's same extension from all sides. Check it punching, I need to know that this is a plane of footing and this is a column. There's critical section around the column where the punching occurs. It is at distance d over 2 from all sides of the column. D over 2. Okay. First of all, I need to determine the Q punch. Q punch, I can determine it by subtracting P column minus Q actual multiplied by the area, which is I'm highlighted in yellow. This area, by the way. This area, I need to subtract this area times the Q actual from P column. Area punch. Okay, area punch, we can determine it. We know that the D from the last step 0.73 meter. So I added to all dimensions of the column given in the very beginning of the example. So I found it like that. These are two values. So area punch is 1.03 multiplied by 1.53. Q actual is equal to what? 23.8. P column is equal to 50. So Q punch, I will find it 212 tons. Stressed punch, Q punch, I will divide the Q punch over the parameter, to determine the area resisting the shear force, the parameter of this, which has I am moving around in black times the depth of foundation. So the parameter is equal to 2 parameter of rectangle multiplied by the depth, which is equal to 0.73. So this value, I found it 57 ton per meter square. I have also here fixed value where which I can compare it to, which is equal to 90 ton per meter square. If it is lesser than this value, so it is okay, accepted. If it is not, so I have to increase thickness. And finally, the reinforcement. The reinforcement area steel is equal to moment critical over K2 multiplied by D. Again, we have to multiplicate the moment 21.7 times 10 power 5 to be kilogram centimeter, K2 given, multiplied by the depth in centimeter. And I found area steel is equal to 19.3 centimeter squared per meter run. I need to check the minimum reinforcement. AS minimum is equal to 0.15% from the concrete area section, which will be equal to 12 centimeters squared per meter run. So I need to convert this value to number and diameter as in the reinforcing RC course. I can use here 8 phi 18 per meter run, and it's not fixed. You can use, by the way, the number ranges from 5 to 10 and the minimum diameter is 12. You can use it 6 phi 22 if you wish. It doesn't matter. You have only to exceed the required area. After determining the area, I can draw the cross section showing reinforcement details, which will be, you have to use your ruler, by the way, to be neat sketch, not as I am drawing right now. I am just drawing a sketch for you. And this is reinforced concrete. You can do the hatching for this, and its thickness 15 centimeter. Thickness for the reinforced concrete was 80 centimeter. The reinforcement is drawn like that, and on the other direction will be dotted like that. You can draw the column drawing, detailing reinforcement like that, and stirrups for the column. Close the cross section showing the reinforcement. This is equal to phi 18 per meter run, and also this is 8 phi 18 per meter run. And if you wish to draw it in the plan, you can also do it like that and draw the reinforcement like that, and write 8 phi 18 per meter run, 8 phi 18 per meter run, and you can determine the dimension 3 meter, and this is 3.5 meter. As I have said, you have to draw it by using ruler, neat sketch showing the reinforcement details. I hope this should be helping to you. The strip foundation, I will send you an example for it. It's so simple. It's the same way as we have already discussed here in the isolated footing, but you have to analyze one direction only, and the other direction we will put the secondary reinforcement by the minimum value only. Hope it's helpful to you, and good luck.